transformations of cubic and quartic functions. So before we start the lesson, we're going to look at different ways that cubic and quartic functions are written. And then we're going to look at the transformed form of a cubic and a quartic function as well. Okay. The transformations we're going to be applying are the same transformations that you saw in grade 11, but now you'll see how they affect the base graph of a cubic function and the base graph of a quartic function. So just as a quick little recall, we looked at how the equations would look like if they're in standard form. So they depending on which function you're looking at, the highest term would either be quadratic, or if it's cubic, there'd be a cubic term, or if it's quartic, there would be a quartic term. In factored form, quadratic functions have 2 factors, cubic functions have 3 factors, and quartic functions have 4 different factors. So we'll see what they look like once you write them in transformed form instead. So also we call the transformed form of a general function. Okay, that's why you have an f here. It's a general function. The variables that we looked at last year that apply different transformations are still exactly the same. So a, which is the value at the front, represents the vertical stretch or compression depending on whether it's greater than 1 or less than 1. And if it's negative, we know that it reflects it along the x-axis, so this is a vertical reflection. The variable k applies horizontal stretches and compressions depending on whether the value of k is less than 1 or greater than 1. And then if it's negative, we know that it's a reflection in the y-axis. And then the value of d applies a horizontal shift left or right. And the variable c applies a vertical translation or shift up or down. Note also vertical transformations and horizontal transformations. When you're looking at vertical transformations, the values are always written outside the brackets. And when you're looking at horizontal transformations, the values are always written inside the brackets. The order of your transformations is important. You want to make sure you stretch and reflect first, so apply any of the values that require you to multiply first, and then do the translations next, so that's the values that need you to add or subtract next. Okay, the graph of a polynomial function of the form y equals a bracket k bracket x minus d close bracket to the exponent n plus c can be sketched easily by applying transformations to the graph of the power function y equals x to the exponent n, where n is an element of all natural numbers. Okay, so natural numbers are just positive whole numbers. So when you're looking at applying transformations to a polynomial function that's in transformed form, what you just need to look at is the base graph, which is just a power function. So depending on what your base graph is, whether it's quadratic, whether it's cubic, or whether it's quartic, you apply the different transformations that you see here to these base functions. Okay? The parameters a, k, d, and c affect the base graph of any polynomial function the same way that you've seen them affect the quadratic function or the root function or any of the other functions that we looked at last year. So the transformations are still the same. They are still applied to the base graph. It's just the base graph will look slightly different. So transformations of polynomial functions. So depending on whether you're looking at any base function, so you would include an f if it's just any base function, or whether you are looking at a polynomial function where you would have an exponent applied. You can look at specific examples of polynomial functions as well. A quadratic polynomial function would have an exponent of 2. A cubic polynomial function would have an exponent of 3. And a quartic polynomial function would have an exponent of 4. And so you can see that they all look exactly the same. The only difference is what the base graph would look like, but how a, k, d, and c are applied to any one of those functions is exactly the same. Okay, transformations of even degree functions. So if you think back to what even degree polynomial functions look like, even degree polynomial functions always have a maximum or minimum point. Okay, so because you have a maximum or minimum point, you sort of have a vertex, an axis of symmetry, and a max or min value that corresponds to it. So remember, since even degree polynomial functions have a minimum or a maximum value, when you have an even degree, so when n is even, the graphs of polynomial functions of the form y equals a kx minus d to exponent n plus c have a vertex at d and c. So here's an example. It's sort of a quartic function that I sketched here. you'll notice that it has a vertex at D and C, so that's the point where the graph is changing directions from increasing back down to decreasing. You'll also notice that there's an axis of symmetry at x equals z, so along here you can see that the graph is symmetrical on the left and right. And then you can also see that in this case we have a maximum value at y equal to c. Okay, so for even degree polynomial functions in transformed form, you will notice that there is a max or min point, just like you've seen with a quadratic function. So for our example, it says for the following polynomial function, f of x equals x cubed, where y is equal to 2 f of negative x plus 6 minus 3. The first part asks us to describe the transformations that must be applied to the graph of f of x in order to obtain the transformed function. So it's asking us to describe the transformations. And so if you think back to what we did last year, anytime you have a transformed function, the horizontal transformations must be in factored form. So the first thing I'm going to do is factor, and you'll see that the solutions are already written for you. The first thing I would do is factor the horizontal transformations that are here, and so I get y equals 2 f of negative x minus 6 and then minus 3. Okay, so now we can look at each of the different transformations that are being applied to the base function and figure out what the transformations are and how they're affecting the graph. So the 2 here applies a vertical stretch to the graph by a factor of 2. The negative that's inside the brackets implies that it's a horizontal reflection in the y-axis. The x minus 6 part tells me that the graph is being shifted, and in this case it's being horizontally shifted to the right 6 units. And then the 3 that's at the end is a vertical shift down 3 units. Okay, so those are all the different transformations that are being applied. Alright, for part B, C, and D, we're going to do this together. For part B, it says write the corresponding equation. So you'll notice that this is right now in a general function form, but it also tells you that the function is a cubic function. So what I'm going to do is replace the f that's in the general form with an exponent of 3 to make it a cubic function. So my function would look like y equals 2 bracket, and I'm going to leave it in factored form. So 2 bracket negative x minus 6 to the exponent 3 and then minus 3. So there is the function in cubic form instead of just a general form. Then the question asks us to state the domain and range. Well, since this is a cubic function, we know that it's going to go infinitely to the left and to the right. So that means the domain would be all real numbers. And the range, same idea. Because it's a cubic function, it stretches from negative infinity to positive infinity vertically, so I know that it's all real numbers for the range as well. Okay, so now the last part says to graph the function using mapping notation. In order to do that, we need to come up with some key points first. So I'll just move that up. So our key points would include some points to the left, some points to the right, as well as the point at the origin that we used to have. So what I've done here is I've sort of set up part of our mapping notation. So our base graph is a cubic function, and I just chose some key points that I can use. So I used a couple of points to the left, I used the point that we had at the origin, and then a couple of points to the right. And what I'm going to do is I'm going to solve for I'm going to determine the corresponding y values just by applying the cubic function that's here. So I have y equals x cubed. So negative 2 cubed would be negative 8. Negative 1 cubed would be negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So there's my key points that I'm going to start off with. And then what I'm going to do is I'm going to apply the different transformations. So looking back up here, I'm going to look at the different transformations, and what you'll notice is horizontally there's a reflection. So that'll make it negative x. And then the graph was shifting to the right 6, so plus 6. So there's my mapping formula for the x values. Then I'm going to determine the mapping formula for my y values. There's a vertical stretch by a factor of 2, so 2y. And then the graph is shifting down 3 units, so minus 3. And so I'm going to apply these formulas to my x coordinates, apply these formulas to my y coordinates, and then I'm going to graph the function to the right. So negative negative 2 is 2 plus 6 is 8. And I'm just going to go through this quickly. You should be able to do the math in your head, hopefully. And any points that don't fit on your graph, it's okay. As long as you have a few points and you can sketch your curve, that's the important part. And hopefully I've done the math right. Did I? Yep. C minus B is 13. There we go. Okay, so I'm going to plot whichever points fit on the graph, and any ones that don't, it's not a big deal. And remember, when you're drawing your graph, to label your axes X and Y. Okay, so I'm going to just go and use a scale of 1s. And I can't plot the first point because it's not going to fit on my graph, but the second point will, so I'll plot the point at 7 and negative 5. And then the next point at 6 and negative 3. And then my next point at 5 and negative 1. And again, my point at 4 and 13 won't fit as well. But I'll know that the graph is going to sort of come down and to the right. And that makes sense because it's sort of going to have a little bit of a change in curve. And it'll sort of look like this. Okay, so there's your cubic function. You'll notice that it's a little bit narrower because it's been stretched by a factor of 2. You'll also notice that it's coming down and to the right, and that's because there was a horizontal reflection which made the graph decrease instead of increase. The graph has been shifted to the right and it's been shifted down a little bit as well. So this point here is actually the point that was at the origin, but now it's sort of the new midpoint that we had there. Okay, so it's sort of in the middle of the graph. Okay, and the last thing I'm going to do is label the graph. So y equals 2, bracket negative x minus 6 to the exponent 3 minus 3. Okay, so don't forget to label your graph as well. And that's it.